Hello everyone, a very good afternoon. Welcome to this video on Bohr's model for hydrogen atom, one of the most important topic in structure of atom chapter. I am Nitin Verma, a chemistry faculty at Infinity Learn by Sri Chaitanya, and again I welcome you all to this topic which is very important from the perspective of JEE mains, advanced as well as NEET exams, other competitive exams for medical and engineering. So if this is your first time here, then please do two things. First, subscribe to our YouTube channel because we always almost daily come up with amazing content, concept questions, PYQs, etc., which help you better your preparation for the exams. And second thing, this is a continuation of the topic. As you can see, this is a part 2 of Bohr's model. So if this is your first time, then after this class is over, I would recommend that you watch the part 1 of Bohr's model because some of the postulates we have covered there, right? So in today's class, we will mainly focus on the energy postulate, which is, you know that the energy is one of the most important properties of a particle, right? So before this, we have finished the Bohr frequency rule, Bohr's quantization of angular momentum, and the radius of stationary states in Bohr's model, right? So today, we will start with the energy postulate, but before that, if you are preparing for the competitive examinations and if you want to give an edge to preparation by joining one of our courses, then you can do so. You will get a straight 40% discount if you use my coupon code, which is Nitin40, right, across all subscriptions, all courses, all things that are available on our platform for your preparation. Okay, so without much delay, let's start, guys. The energy postulate. Okay, so you know that as per the Bohr's model, electron revolves around the nucleus in concentric circular paths, which we call orbits, and because the energy of the electron is fixed in an orbit, we also call these orbits as stationary states, right? Because the distance is fixed, distance of the electron from the nucleus is fixed as long as it is in a particular orbit, and also the energy. Is that clear, right? Now, because electron is a charged particle, okay, nucleus is also a charged particle, and electron is going round and round as per the Bohr's model, right? So we can say that the Coulombic force is equal to the centripetal force, right? What is the Coulombic force here? Proportionality constant K, which you all guys know, it is 1/4 pi epsilon naught. Then product of the charges, one charge is nucleus. If Z is the atomic number of the atom, and you guys know that the magnitude of charge on a proton is equal to the magnitude of charge on the electron, right? So the charge, total charge on the nucleus is Ze. All right, guys, the charge on the electron is -e. Let us put it along with the sign, right? Sign of the charge divided by the square of the distance, right? Which distance? From the center of the nucleus till the electron, right? So this is the radius of nth stationary states. Okay, guys, this is your Coulombic force, Coulombic attractive force, right? And this is equal to the centripetal force, which is mv square by r, again where r is the distance, radius of the state, m is mass of the electron, because we consider the nucleus to be stationary here, and v is the velocity of electron. Is that clear, guys? Okay, now we can do some simplification over here. First, cancel out r, okay, and multiply and divide this equation by 2, like this, right? Then you can easily observe that this is equal to the kinetic energy, half mv square is equal to the kinetic energy, and this, guys, if you see carefully, it is the formula for the potential energy of the system, right? When you write the expression for potential energy, it is exactly equal to the Coulombic force, except in Coulombic force it follows inverse square law, right? So we write 1/r square, but in potential energy it depends inversely on the distance, right? So there is not r square, it's just r. Is that clear, guys? Right? So this is k Ze minus E divided by r. So this is potential energy, right? Negative sign I'm putting there, and this is equal to the kinetic energy of the electron, right? And 2 is there, right? So we end up with this formula that potential energy, I can rewrite this formula as potential energy of the electron is the negative twice of the kinetic energy of the electron, right? So for a charged particle which is performing a circular motion, we can say this, that the potential energy is negative twice of kinetic energy. Is that clear? Okay. Then another thing is that the total energy of the electron, right? Electron is bound to the nucleus, it has some energy because it is moving, right? So the total energy of the electron, we write it as En. Okay guys, we write it as En, that is the energy of electron in nth orbit. Okay, now obviously it is equal to the sum of kinetic and potential energies. It is equal to the sum of kinetic and potential energies. Okay, so I can write it as kinetic energy is this. What is potential energy equal to, guys? This is negative twice of kinetic energy, and hence you can say that this is equal to negative of kinetic energy. Okay, right? So the total energy of the electron, which we denote by En, it is equal to the negative of kinetic energy. Okay, now you guys know that kinetic energy is positive, so the energy of electron is always negative. This is something we should remember. Okay, so energy of electron is always negative if it is bound to the nucleus. So you may think, what does it mean? What is the meaning that energy of electron is negative, right? So what happens when electron is not bound to the nucleus? Okay, we will see this a little later using mathematically using a formula, but for now let us understand that when an electron is not bound to the nucleus, we assume that the electron is at rest and its energy is 0. Okay, an electron which is at infinite distance from the nucleus, it is assumed to be at rest, its energy is taken to be 0. Now you imagine if this electron is pulled closer to the nucleus. Earlier it was at infinite distance, so its energy was 0. Now it is under the influence of this nucleus. Now because of the attraction between the electron and the nucleus, what will happen? What will happen? Its energy will decrease, right? It will have a negative potential energy. At infinite distance, the potential energy was 0. Why? Because R was infinite. R was infinite, so potential energy is 0, 1 upon infinity is 0, right? So, but when the electron is under the influence of the nucleus, then the energy decreases, potential energy is negative, which is why the energy of electron which is bound to the nucleus is taken to be negative. Okay, so let me just summarize. The energy of a free electron is taken to be 0, it is assumed to be at rest, no energy. And the energy of a bound electron is taken to be negative. This means that a bound electron is more stable than a free electron. Is that clear? So these are the two things that you should remember. First, potential energy is negative twice of kinetic energy, and the energy of electron, the total energy of electron, is just the negative of kinetic energy. Is that clear, guys? Okay, now let us write the expression for this. So can you guys tell me what is the expression for the energy of electron? What is the expression for energy of electron in hydrogen atom? It is negative of Rydberg constant, right? Z square divided by n square. So this is the formula that you guys should remember, because using this formula alone you can solve a lot of questions. You don't have to remember many formulas, right? So the energy of electron in nth orbit is negative of Rydberg constant. We will come to that. Z is the atomic number, guys, because you know Bohr's model is applicable to hydrogen like species, right? Helium ion, Li2 plus, like that. N is the principal quantum number. Okay, and R, which is RH, is the popular Rydberg constant. What is the value of R, right, in terms of energy? Obviously it's a constant, its value will vary depending upon what unit you choose, right? So one value is 2.18 into 2.180 into 10 to the minus 18 joule per atom. This is per atom, right? Then you can divide it by the value of electron volt. 1 electron volt is how much? It is 1.6 into 10 to the minus 19 joule. Okay guys, so if you convert it into electron volt, this comes out to be 13.6. You can do that, it's a simple exercise. So the value of Rydberg constant in terms of electron volt is 13.6. Okay, then you can further convert it to kilojoule per mole, because we'll see later that this formula can also be used to calculate the ionization energy, right? So in terms of kilojoule per mole, this comes out to be approximately 1312 kilojoule, right? And then you can convert it to wave number, right? E is equal to hc by lambda. You can convert to wave number, wavelength in whichever unit you want, you feel like, okay, right? So, but these are the three values that you guys should remember. They are very frequently used, okay? Now, here you can see if an electron is at infinite distance from the nucleus, what is the value of n? If an electron is at infinite distance from the nucleus, what is the value of n? It is infinity, okay guys? What is the value of n? Infinity. Then what is the value of energy? Tell me, right? It is minus RH z square divided by infinity square, so it will come out to be 0. That is, the energy of an electron which is at infinite distance from the nucleus is 0. That is, the energy of a free electron is 0. Is that clear? Okay. Now, supposing electron makes a transition, okay? Electron makes a transition from n1 orbit to n2 orbit, right? Initial orbit is n1 and the final orbit is n2, okay? What is the energy of electron in this state? It is minus RH z square by n1 square. Clear guys? What is the energy of electron here? En2, it will be minus RH z square by n2 square, right? So how much energy is needed to make this transition, right? Initially, let us suppose the electron is in this state, it wants to go into this state, right? So how much energy should we give so that it is able to make this transition? So how do we do that? Obviously, the amount of energy needed if it jumps from n1 to n2, or equivalently the amount of energy released if it jumps back from n2 to n1. This is obviously guys final minus initial, right? This is obviously final minus initial. So this is equal to how much? This is minus Rydberg constant z square by n2 square, and this is equal to negative of Rydberg constant z square by n1 square. Okay, so this negative will turn positive, and you can see very easily that we can take two things common, right? Rydberg constant and z square. So you can rearrange it, you will get this formula RH z square, that is the atomic number of the species, and then okay, so this is a very important formula guys. This formula you will use to calculate the energy absorbed or released when an electron jumps from n1 to n2 or back from n2 to n1, right, whichever the transition is. And you don't have to remember a lot of values, okay? You guys know that energy is equal to h nu, right? Planck's equation, energy is equal to h nu, it is equal to hc by lambda, and it is equal to hc nu bar, right? So you can use these relations to calculate frequency of the photon which is absorbed or emitted, or wavelength of the photon, or the wave number of the photon, right? And let me make your work a little easier here. The value of hc in SI units is approximately 2 into 10 to the minus 25. This I have also told before, it comes handy sometimes. In SI units, the value of hc is 2 into 10 to the minus 25. Is that clear guys? Okay, so I hope this part is clear. The energy change when an electron makes a transition from one orbit to another. Is that clear, right? So let's take a question. Think about it, how to solve it. The kinetic energy of an electron in the second Bohr orbit of a hydrogen atom is what? The expression. This is a previous year question. See, for that we'll invoke the Bohr's quantization of angular momentum, okay? Right? If you have forgotten, then I'll write the expression here, and for details you should go back and watch the first video on this topic, which is available on our YouTube channel. So MVR is equal to NH upon 2 pi, okay guys? As per the Bohr's quantization postulate, only those orbits are allowed in which the angular momentum MVR is an integral multiple of NH upon 2 pi, okay? From here, I can rearrange this expression for velocity, guys, okay? So the velocity is NH upon 2 pi mr. Fine, okay? Now you guys know that the expression for kinetic energy is half mv square. It's simple. Where the mass is of electron, velocity is of electron, okay? So basically I need the formula for v square, okay? So if v is this, what will be v square? V square will be n square h square upon 4 pi square m square and r square. So far so good, right? So this is the expression for the square of velocity. Now which orbit are we exactly talking about here? Second Bohr orbit, guys, and the answer is in terms of Bohr radius a0. This you can see, right? So what is the formula for radius? Guys, what is the formula for radius? The formula for radius is a0 n square by z, okay guys? The formula for radius is a0 n square by z. Now we are talking about second Bohr orbit, so n is equal to 2, and for hydrogen z is equal to 1, okay? So this simply comes out to be 4a0. Is that clear? Right? It simply comes out to be 4a0 because the value of n is 2, second orbit 2 square is 4 and z is equal to 1. So let us substitute this value. Okay, so the kinetic energy of the electron is half m, right? Half m, v square, n is 2, so 2 square is 4, guys. So this is 4h square divided by 4 pi square m square, and r square is how much? It is 16a0 square. Okay, so you just have to do one thing, you have to simplify this and you will see. Just do this, I'm right here with you. What does the answer come out to be? So you would have calculated that it comes out to be 32, right? So this is 1 power of m, so this is h square, and this is 32, this is pi square, this is m, and this is a0 square. So this is our correct answer. Is that clear, guys? Okay, so this becomes our correct answer. Understood? Okay, so let's take one more example. The energy of electron in the first Bohr orbit of hydrogen atom is minus 13.6. That we know, right? Because the energy is equal to minus Rydberg constant, which is 13.6 electron volt. Z square is 1 for hydrogen, obviously, and for the first orbit it is 1 again, right? So it is minus 13.6. That we know already. The possible energy values of the excited states for electron, right? You have to calculate the possible values. So obviously this is E1. Let us calculate E2. How much does it come out to be? Minus 13.6 electron volt divided by 2 square, right? Because n is equal to 1 is the ground state. Always remember for hydrogen atom, okay, right? Because that is the least energy state, it will be most stable. So that is the energy of electron in the ground state is 13.6. Least energy, consider the negative sign also. In the first excited state, n is equal to 2. So what does this come out to be? It is 13.6 divided by 4. So I think it will be 3.4 electron volt. Is that clear, guys? So this is one possible value of the electron in an excited state. So minus 3.4 electron volt. Clear, guys, so far? Let us calculate E3. So it is minus 13.6 divided by 3 square this time. Okay, so this is 9. So how much does it come out to be? It is minus 1 point approximately 5 electron volt. Is that clear? Okay, so the first value of excited state is that is minus 3.4 and the immediately next value is minus 1.5. Okay, so obviously these values cannot be possible, right? The energy of the ground state is 13.6 and the first excited state is 3.4. So this is ruled out, guys. It's not possible, right? And the next value is 1.5, so this is ruled out. It cannot be. So the answer is option A and option D. It is a previous year IIT advanced question, multiple option correct type. Is that clear, guys? I hope you guys understood. Let's take up next question. This one is a little bit calculative. The electron energy in hydrogen atom is given by this formula. Sometimes they give you the formula, right? So we don't use what we already know. We just we apply the value using this formula, okay? So the electron energy in hydrogen atom is given by this. It's in CGS unit, you can see that, right? There are two parts in this question. First is calculate the energy required to remove an electron completely from n is equal to 2 orbit. Now if you look at this part carefully, this question is asking about the ionization energy, right? See again, electron is initially in n is equal to 2 orbit. We want to remove it completely. So obviously we are trying to ionize the atom, okay? So for specifically for ionization energy, there is a very simple formula. It's very easy to derive. Let's do that right now. N1 is 2, right? Electron is initially in second orbit, okay? So let us first derive the general formula, okay? Let us take it n only. N1 is n, okay? And N2. Finally, the electron is taken out of the atom. And always remember, if the electron is no more bound to the nucleus, n is equal to infinity. Is that clear, guys? Okay. Now, the value of energy will be what? It will be RH Z square 1 upon N1 square minus 1 upon N2 square. Remember, we just derived this formula a few minutes ago. The value of N1 is n. The value of N1 is n and the value of N2 is infinity. 1 upon infinity is 0. It's very easy, guys, okay? So you can see delta E is equal to RH Z square by N square. A very simple formula for ionization energy. Is that clear, guys? A very simple formula for ionization energy of an electron. So if you are taking an electron out of the atom and if the electron is initially in nth orbit, right, the value of n is 1, 2, 3, it could be any integer. So the energy required to remove that electron is RH Z square by N square, okay? Now if you look at this value, this is exactly equal to the electronic energy in magnitude, right? The energy of electron in nth orbit is minus RH Z square by N square and this value is just negative of that. Is that clear? Okay. And we also remember that the electron energy is just the negative of kinetic energy, right? Okay. So kinetic energy will be negative of electronic energy, which is basically this expression, okay? Right. So these are just some relations which you should notice, right? So the ionization energy of electron is equal to the kinetic energy of the electron, right? Is that okay? So electron has some kinetic energy. If it comes out of the atom, then its kinetic energy is 0. So basically we have to provide that energy, right? Okay. So you can find that out. The value of RH is given. The value of N is 2. You just substitute 2. So it will be this value divided by 4. Okay. So let's do it. So this is your ionization energy, okay guys? And the second part was, what is the longest wavelength in centimeter of light that can be used to cause this transition? Very easy. This is the ionization energy. I can equate it to Hc by lambda, right? Because the question is, what is the longest wavelength? Is that clear, guys? So the wavelength is Hc by ionization enthalpy, right? Because the question is in centimeter. You have to calculate the wavelength in centimeter. So just take CGS units, okay? So the value of Planck's constant is 6.626 multiplied by 10 raised to minus 27, okay? Arc second. It is in CGS unit. multiplied by the velocity of light is 3 into 10 power 10 centimeter per second. I am taking all CGS units, okay, and divided by this value, ionization energy. So you can work out this calculation. It's very straightforward. You will find out what is the wavelength in centimeters. Is that clear, guys? Okay. So that's all for today's class. See you in the next class with the remaining postulates of Bohr's model. And meanwhile, if you're preparing for any exam, you want to join, you want to prepare with us, with the expert teachers at Infinity Learn, you can join our courses, you can take subscriptions for your doubts and etc. You will get 40% discount, okay, using my coupon code. So that's all for today, guys. See you soon. Take care. Bye bye.